Okay, so there's the operations, NQ, DQ, how many people are standing in the line, who's the first one in the lineup, and who's the poor person who's stuck at the end of the lineup. Okay, so now let's talk about how we would store stuff. Okay, so the first way that we thought of storing stuff all the time is to say, let's use an array, and I'm going to just draw it horizontally because that's the way we think of lineups. Okay, so there's our lineup of people, and we've said, we're thinking, okay, we'll go along and we'll add people into the array like this, okay, like we've traditionally done. Okay, so now all of a sudden somebody says, go get me the first one out of here. Okay, first one's now gone. What did we do with our list code?
You had to shuffle everybody.
Had to shuffle everybody down. So if we again imagine that this has got 10,000 people standing in the lineup, then we got a little bit of a problem here.
Could we just track who's in front of us? Like each kind of node tracks?
Well, we don't have a node yet. This is an array, remember?
But like, could we not use an array?
Well, we're stuck with an array. We'll do a linked list later.
Okay.
Like we're going to do more than one way of doing this. Okay? So let's just try to figure out how we would do it with an array and be efficient. Right? The issue that you run into is that adding to the end of this lineup is fine, but every time you remove somebody from the beginning of the lineup, then the whole world shuffles, which is physically what happens in real life, right? I mean, you're standing in a lineup, there's 10,000 people in the line, and the first one goes, everybody takes one step forward, but that's not particularly efficient. Okay? So one of the things that we could do is we could just say, oh, okay, well, all it will do is we'll remember that this is the first, and now we'll just take this one when somebody asks, and we won't bother shuffling. Play that game. But now what do you do when you go to add somebody else? The tradition that we had was to say, well, we'll expand the array. But that means that you now have this ever-expanding array with a whole bunch of stuff at the start that you never use again.
You could loop it.
So what do real people do? Real people turn around and go, oh, well, look, I've got all of these unused spots. So if I ever hit the end of this thing here, we'll just play the wraparound game and we'll start filling spots in here. And as long as you don't have, you know, these two things colliding, right? You don't try to put too many people into the queue, then you can just keep wrapping it around and life is good. Okay? And queues are sort of like stacks. When people make them, they traditionally think of them only as being a fixed size. So it's not really a surprise to not have to worry about the size. Right? So the same with stacks. If people really want to, we can make our API so that the constructor takes in the maximum size of the queue that you want. Okay? So all that we need to do here is to play the wraparound game in order to make this thing work. Okay? And so notice there's still this idea that there's somebody trying to process these and make these go away, and in the meantime somebody's busily adding on to the end and basically trying to make the two things collide. Okay, so in order to do that, there's our queue with an array underneath. We're going to need a private items array of E-type things, and I guess I should do the Java thing and put it on the correct side. Okay. And we'll initialize that thing. Items is a new, here's where we have to say object
This is in the queue function.
array of, oops, sorry, need a constructor. So public queue array. And we'll do the items is new. And this is the game where we have to play of make an object array of some particular size. We'll make it small just so that we can see things happen. And then we have to do the silly cast to say it's really E-type things. Okay, that takes care of that. What's the other information that we have to keep track of?
Current position.
The front of the queue and the next free at the end.
So there's actually two interesting things here. If I do a diagram that looks like this in the easy middle case, there's where am I going to add the next one to an empty, and there's also what?
The next one's a quick up.
This one, which is the
Next first line.
first, what's the interesting thing about it? It's the first full one, right? So this is the empty position versus this one's a full one that somebody's going to grab. Okay, so I'm just trying to make sure we have the word empty and full someplace in the variable name to give the correct sense of what those things are being used for. So we've got private int empty, and now what do we want to call it to make it more obvious? Empty position, and it's the next empty versus private int first full position. Okay, so next empty position needs to start out at 0, and first full position
No.
needs to start out at
-1?
No. No.
-1.
you know, the traditional thing would be to do that, to say that it's 1 before the place that we really need. I always get reluctant when I see that in modern code because it's a bit of a cheat in essence that sometimes catches you. So let's just leave it at 0 for now and see what happens. Because you're really not supposed to be able to ask for something unless it's there. Okay? So by the way, what is size going to return?
No, next empty.
Next empty position -1.
No, because you have to have, it would be next empty position minus full
It's
position.
like a wrap function.
Well, in this case, it's 6 minus 3 maybe gives us 3, and
But if
we're
the-
lucky.
if the
But
next
if they,
empty is-
but if they wrap around,
Yeah.
then all of a sudden that might not work, or it might work if we take the absolute value plus or minus 1, whatever it happens to be. Okay? If you look at traditional computer science code, they'll get back to the point of going, oh, I don't want to use that extra variable. I can calculate it in terms of last empty and next full, and I can go to the trouble of figuring out in my head what it's supposed to be. But the easiest thing to do here is to forget about it entirely and just say, well, if we were to keep track of the number of items we had, then we would never have to worry about it. So rather than worrying about doing the weird calculation, whatever it happens to be, I'm just going to keep item count. And every time something comes in, I add 1, and every time something goes away, I subtract 1, and there's no doubt at all about what it is. We don't have to sit down and explain the math to people and draw the diagram. Okay? So this is another case where just adding that variable in the long run makes your life easier and makes the code a lot easier to understand. Okay?
Initialize.
So we'll set item count equal to 0 also. And now what happens when you NQ?
You add 1 to item count.
Before that,
You add it to the next empty position.
items sub next empty, and notice the variable there says, okay, well, it don't make sense to add something to an empty position. Holds on to that item, and then next empty position goes up,
Item count goes up.
and item count goes up. And I'm just going to separate those two ideas. Okay.
And we can do something with first full. Maybe not with a Q number. Never mind.
How about DQ?
If you try to process something before they run its empty, that's gonna happen.
You're not allowed to process something until you actually have something to look at. Okay, we can always handle the cases, the special cases, but basically you're supposed to not abuse this thing and only ask for things when you have them. That's why we're providing size.
So DQE would get the item at the first full position.
So the item that we're interested in is the one that's at items sub first full position. Notice how easy that is when you have the variable name, and that means we'll send that thing back. And then we'll go in the middle and figure out how do we have to make the variables right. So what needs to happen? First full position needs to go up. Needs to go up, and item count needs to go down.
We also need to check to make sure that the first full position goes above the size.
Oh, we're not worrying yet,
Okay.
okay? So the,
Remove it?
huh?
Remove it all, or?
It'll be overwritten. Didn't notify, but.
Well, we can worry about that later. I mean, again, the game we're trying to play is always think of just the regular rose-colored glasses case, which is assume that this array is 10 million items long, we're never going to run off the end, life is going to be good, get that case to work out first, and then we'll come back and we'll start to worry with the if statements. Okay, so we've got that done. What about peak first?
It would be the same code except.
It's the one that's at the first full position. How about looking at the endmost item?
It would be the last, yeah, the first position, minus one.
It would be return items sub last empty position, or next empty position, minus one, which again makes sense, one before. Okay, something that looks like that. I made some tests, and so I checked to see whether or not the queue was initialized. I tried to NQ1 and DQ1. By the way, these are the stack tests that I just stole and changed the order that things appear. So this is now first in, first out. So I NQ'd two, so I put A and B on. A should be at the start. If I DQ, I should get A, and that should still leave B sitting there. Okay, so I more or less borrowed the same things. And we'll run the test, and oh look, it magically works. Okay, except what's missing from the unit tests. I didn't test peak last because I forgot about it, and what else?
You can fill up the array,
There's nothing that tests the fill up
or if the array is empty.
thing. Well, we're not going to worry about empty because they can't get at it unless they're, normally the way these things work is that you're supposed to inquire about the size first and make sure that there's something there before you do a DQ. Okay, so it's impossible, it should be impossible to turn around and ask for something that's not there. Okay. Okay, that's not bad. How are you going to write a unit test to see whether or not the wraparound works, which we know it doesn't?
Like a for and a couple instances.
You can write a tracer.
Just with the API that we've, well, okay. There's two ways of doing it. We looked at it, the same thing, we had the same issue when we looked at the list. There's a little bit of an issue with checking wraparound. How would you know how big it is?
We wouldn't decide to.
You
can't get at.
You could get the size of the array, but we didn't make that item known. Okay? And we're not making the positions of things known. So the only way that you can really test this thing is just basically to abuse it by adding, you know, 1,000,000 items. And if you can put 1,000,000 items on and get them off in the correct order, then probably life is good. Okay? But it's actually really difficult to test that externally unless you have some internal knowledge of how it actually works. Okay? So what we'll do here is we'll just add and subtract a bunch of items eventually. Okay, so let's get back to this NQ and DQ and talk about how you handle the wraparound. What code do you have to add here? What's going to go wrong in this code?
It's going to run off the end of the array.
It's going to run off the end of the array because what variable is going to go wrong? This next empty position is going to go bad. Okay, it's going to hit the end of the array. So you would add something in here that says
Check this going.
if next empty position, oops, position has gotten greater than or equal to items.length, which is the actual capacity or the end of the array, then what would happen? Then next empty position becomes equal to 0. Where would you have to do that? Where else would you have to do that? First full position also does the wraparound game. So maybe this, since we're going to, now what you want to do, I just know you want to copy and paste that, right? Okay, which is now the worst thing that you can do if we made a mistake with that. So the best thing to do is to write private int wraparound, where you pass it some position, and it basically take that code and hide it inside here, and just change that to position. And then we'll just send back whatever number that happens to be. Okay, which now allows you to go in and replace, we have to do position plus plus, sorry. So we'll increment the position. If it's gone too far, we'll set it back, and then we can change this code to say next empty position is just the wraparound of whatever the current position happens to be, which is also next empty position. Okay, so there's that idea. Be very careful about copy and paste of code. You're almost always better off to play that game, because now we can go into the other places in the code and we can just say, okay, well, first full position is now the wraparound of first full position. Okay. Notice the one case that is going to be a little weird is that one, but I'm not going to worry about that one for now. Okay. This is the easiest way to understand wraparound. There's a shortcut for doing that. Remember your assembly language integer division? No?
Shift.
By something other than 2? What happens when you do assembly language division? What do you get as a result? I have to go back to primary school for this one.
Is it doing modulus?
So 15 divided by 2 is 7, and then
0.5.
not really, go back to primary school.
Remainder 1.
Remainder 1. Okay, so integer division results in 2 pieces. It results in whatever that thing is called versus the remainder. Okay, and so when you do integer division traditionally, that's what you get as the result in your register. The remainder comes when you do 15% 2, which is the mod function, and then with that, you get the other piece back. You get the remainder piece back. What's the interesting thing about that remainder? Always less than whatever you divided by definition, because that's why it's a remainder.
So wraparound just return position
Okay.
plus 1 modulus items.
Yeah, so you can replace all of this code with something to the effect of return, well, we'll do it this way first, position plus plus, and then return position mod items dot length. Something along that line. Okay, so we'll just block comment that one out. Okay, so increment the position, then take the remainder of that thing, whatever it happens to be. So the joy of that is that if the number is less than the size of the thing, then you just get the same number back again. And if it's greater than, then you get the remainder of the division. So it just magically works. Okay? The only problem with that is that nobody other than mathematicians ever understands the mod function, and computer programmers are probably normally used to seeing this sort of code, even if it's a little bit longer. So it's just more obvious to most people to probably just write it that way. Oh, we've hit the end, let's go back to the beginning, which is what that code says.
It's not really necessary either because you're only going up by 1. If you're going up by more than 1, then it would be more important.
Yeah, if you're going up by more than 1, you'd end up having that. That wraparound function, by the way, that mod function, we'll come back and we'll use it later in the term for a more interesting purpose. Okay, so this one isn't the most useful purpose for it, but, okay. So I just like this code because I think it happens to be just a little bit more obvious than the mod function, okay.
Position plus plus though.
Yeah, I forgot the position plus plus. There we go. Okay, so something along that line. So the point of this exercise was, again, more of an efficiency thing to show you that, I mean, the queue is a relatively simple thing, but you need to understand that there's a good way of manipulating the array in order to keep it reasonable. And as long as you don't ever overfill the thing, life is good. Okay? So tomorrow what we'll do is we'll play the same game, only we'll use linked lists to manipulate this queue instead. And we'll see you in the lab.